welcome everyone. I hope everyone can hear me. My name is Natan Silnitsky, and I'm a backend infrastructure team lead at Wix.com. And Wix has a huge scale of traffic with more than 500 billion HTTP requests and more than 15 billion Kafka business events every single day. And this talk is about three caching patterns that are used by Wix's 2,200 microservices in order to provide the best experience for our users, while also making sure to reduce costs and also increase availability. And one of these patterns was actually developed by my team, Data Streams team at Wix Backend Infrastructure. So I'm really excited to share that pattern with you and the rest. So let's start. A few words about Wix. So Wix is a website building platform where you can manage your online presence and also manage your business online. We have more than 200 million registered users from 190 countries and more than 100 million websites running on Wix, more than 5% of all internet websites. So let's see a few issues that Wix developers are faced with from time to time. We have Rebecca from Wix Stores, and she's in charge of Stores checkout service. Now, Stores checkout service requires to fetch some app identification information from the Wix app market. It does that when Stores checkout service starts up, and it is required in order to be configured correctly. But what happens if the second party service is unreachable for some reason? Maybe there's network connection problems, or maybe even Wix app market service is currently down. Um, that if we don't deal with it, it means that Stores checkout service will also be down because it doesn't have the information required to start up correctly. Another use case from Wix Stores from the e-commerce solution is with Alex. Alex is in charge of the Stores catalog service, and here it uses a database, Stores catalog, where it keeps all of the catalog products, etc. And recently, Alex has noticed that there are database latencies and even failures for certain queries, like in high percentiles, meaning that users will sometimes in high percentiles not get the best experience they can. So that's a big issue, and Alex would like to resolve that. So as your traffic grows and increases, so will the time it takes to, so will the loading time, the overload on your system, response times increases, latencies, and also network costs will increase because you do a lot of networking all around your system in order to fetch all the data that is required. And you may end up with database failures due to high load on database as well. Now, if you do introduce a cache, it means you will definitely reduce latency as long as there will be a cache hit most of the time. And you also reduce the needed scale of your system. So you don't need as many service instances or Kubernetes pods as when you don't use a cache, because the cache will be the source of the response, so you don't need to go all the way to other parts of your system. And it also improves reliability because using a cache is much easier than doing complex operations, and it's much simpler and faster. So overall, you will definitely increase the reliability of your system, even if, let's say, some database is unavailable. If you have a cached response, that doesn't even matter. So let's take a look at a few of the use cases we have found at Wix, and what kind of caching pattern we can use for them. So the first one is the high risk or cost of network failure. And that's like the example I showed in the beginning, where you want to start up and fetch information from remote sources, but they may not be available to some network error. So here, caching external critical configuration data, data that is required for the actual running of your service, is really key. Now, the second use case is a bit more generalized and a bit more ubiquitous, and that's to improve the average latency for data layer access. So all our services usually have some database layer, and as usage grows, so can issues and speed really deteriorate the latency for retrieval of information from the database. So at Wix, we use a combination of a cache combination of DynamoDB as a persistent layer. And on top of that, we have an in-memory LRU cache per service instance, and it is populated by fetches, but also by a CDC. CDC is the ability to get stream of events from any time your database gets updates. Don't worry, we'll cover that in depth in a little while. Now, the third use case is when you have some very high external traffic cases, where you have external traffic like browser HTTP requests coming into your data center with all of your services deployed, and you want to provide the fastest HTTP response back. Maybe like rendering, where you need to provide back HTML and stuff like that. So here you would like to put a cache before your service even, not in the middle or something like that, even before the request comes into your service. So it serves as a proxy to your service, and it may be possible to actually avoid going into your service if there is a cache hit. Now, while we discussed patterns, use cases where we don't want to use any cache, it's also important to understand when not to use caches. So if you have a very young product, let's say you're working on a prototype, you're starting to test it out in the market, and you don't expect to get like huge traffic on the first few weeks or even months. So I wouldn't architect this product with a cache built in all from the beginning, right? Um, because caches do add complexity to your architecture. Especially tricky is all the area of cache invalidation, making sure that you don't have stale data that can really hurt what you're trying to test with your proof of concept like prototype, right? So be careful not to use a cache when you don't really need to. Okay, so now we're going to delve into each of these caching patterns in depth so you really get a good grasp of why they are needed and how are they implemented. We're talking about the S3 backed static cache, so a simple object storage, cloud object storage that can really help us be served as a cache. We also have the DynamoDB plus that database events streaming and all of that area cache. And we have the HTTP reverse proxy cache. So a proxy before your service that actually tries to eliminate traffic to your service. And we'll start with the first one, of course. Um, so we're going back to the issue I talked about at the beginning of this talk about how to make sure that service overcomes unreliable requests, especially when it needs to start up with some external configuration data. So at Wix, we have a library called Koboshi, or Remote Data Fetcher, that it is set up with the user handler code how to fetch external information. So our e-commerce service will fetch on its init of Koboshi, it will fetch app definitions and all kinds of other configuration data that it requires from Wix App Market. So Koboshi will, at first, will try to fetch the information from App Market if it does not exist yet in Amazon S3 Cloud Object Store. And if it does exist there, it will first fetch the information from there, and that way it will guarantee the high availability. Now, if you are not using Kubernetes as your deployment platform, then you can actually use the local disk and just persist data there in Koboshi. So it's really a matter of whether your disk actually belongs to the service in the long run, or like in Kubernetes, where your local disk keeps getting unmounted from your pod, and your pod gets recycled and stuff like that. So you can't really rely on a long-term disk for your service instances. So for that, we actually use AWS S3. Now, if Wix upmarket is down, like I said, Koboshi can, when the e-commerce service starts up, it will get the information from AWS, and then it will periodically try to fetch information, because potentially there could, at some point in time, be an update for this configured data, even though it's mostly static. But once Wix app market connectivity gets up and running again, then the AWS bucket of information of the cache will be updated if that's needed, if there's some new information there. So to summarize this pattern, we're talking about the type of cache that is read-through. A read-through cache means that you don't access the source of truth data by yourself. The cache will access the data for you, and you just ask it to retrieve. So it will retrieve something from its own store of data, or it will retrieve it from the external source of truth. So they put a read-through cache like this, like Koboshi, before the third-party service. Now, it's important to understand that you can only use this type of cache if the data can fit into memory. I mean that if you have like terabytes of data that you need to load at the startup, that may be a problem. So this won't be a good fit. But if your data can easily fit into memory, then it's really a good fit then. So like I said, it's best used for external source of static configuration. Sorry about that. Okay. So what I won't use this type of cache pattern for is if you have really highly dynamic updating data that keeps getting changed, like you have a key, but the value keeps getting changed. So this really is not a good fit for it, because it's more for like startup loading time. You don't want to have like a fast polling done all of the time, because it can really affect the performance of your app, basically, and it will be not really wise to actually cache this sort of information. So it's really more for statically updating data, really usually quite stable type of data. Okay, so next we're going to discuss our DynamoDB database solution for reducing database latency. So here we have the example of a store's catalog service that fetches information about catalog products from the store database, and it got more and more slow as traffic increased, and the owner decided that they want to put a cache here. So how did they introduce the cache? So they use our own library for this. It's called the cached key value store. And the way it works is that the service first writes new information and updates to the store's database catalog database. And then it will also put information in the cache. So this is like an LRU cache, least recently used items are evicted when the size reaches the limit. And the data is stored here. Now, when the service tries to retrieve information, it will first retrieve it from the cache. And only if there's a cache miss, if the information is not there, it will try and read it from the database. So as long as, statistically, most of the time, there's a cache hit and the data is found in the local in-memory LRU cache, then we're good to go. But we have a lot of instances for our service. So traffic is spread around among them. So the fact that we have a local in-memory cache will not be very useful, right? We probably have a lot of cache misses. So we don't only put the data into the local in-memory cache, we also put it into Amazon DynamoDB. So it is persisted and everyone can access it. Now, we chose Amazon DynamoDB for key values, cached key value stores because they have great cross data center data replication and great conflict resolution. So we can actually have data synchronized geographically all around the world, and conflicts will be automatically resolved. So it will be eventually consistent. And you can also put as much information as you require. There's no limit here for this cloud type of database. And now let's think about, okay, so we put information in database, but how are we going to update the rest of the instances that have not received this cache update? So we use Amazon DynamoDB's events. We have DynamoDB events. So we migrate, we convert them to Kafka events because at Wix we use Kafka. Sorry. And we have this dedicated topic per DynamoDB key value store table. And it has all of the updates done to this database, one after the other, sequentially per partition. So we know that the same key will always be updated sequentially. And now we have the library that stores the in-memory LRU cache also has a Kafka consumer. And it consumes the information from the CVC topic, from this dedicated stream of events from the database. And it updates the in-memory cache. So all of our service instances get automatically updated no matter which of the instances has actually done the change, which is great. And of course, if the key already exists, it will just update for the new value. So if key 1 before had the value of V1, now it is updated to V2. Now, there's also the question of what happens when a service restarts or has a new version being deployed. Well, potentially it will start off with a completely empty in-memory cache. And that will mean cache misses. So we'll have cold cache and we'll much worse latency because we need to go to the database. So in order to solve that, when the service starts up, the library first consumes all the most recent events from the Kafka topic in order to have the ability to return cache hits. And because it's the most recent events, there is more likelihood that there will be a greater percentage of cache hits because of the temporal rule of caching. Now, there's also the option to take not only the most recent events, but the entire Kafka topic. And that's because Kafka has a mode where you can keep a topic as a key value storage of its own. It's called a compaction, log compaction in Kafka. And in case you have, you know that at least for now, all of your data can fit into memory, then you can set this topic as being compact. And the library will first fetch all of the events from the compact topic and fill up your cache, meaning that you'll have 100% cache hit ratio, which is great. Now, with Kafka, it's important to set up that it aggressively cleans up stale values, so it won't take too long to read all of the partitions sequentially. But as long as you do that, you're going to have fast startups with 100% cache hit, which is great. Of course, if you have a situation where your data set is increasing and it's going out of the amount of memory that your instances can take, you can switch back to being a non-compact topic, a regular topic, and just take the most recent events. So of course, there's a trade-off here because you won't get 100% hit ratio, but when you have so much data in your data set, you really can't expect to get 100%. So you can play around with the amount of events that you're going to get a warm up and hope that you will get a really, really high percentage of hit rate ratio. Okay, so to summarize, we're talking about usually a cache aside kind of situation that you put before your database in order to have fast access times. But it can also be a cache on its own, like when you want to use it as a key value store, let's say. You don't have to use a database separately. This can be your database with a built-in cache, which is great as well. And here we don't have limitation on the data size because we have a configurable LRU in-memory cache, and any data that doesn't fit in there will get discarded. So we don't have that problem anymore. We traded off this with, of course, the hit ratio, right? And so it's great for getting faster access to databases, and when you want to have a simple key value store with a cache built in on top of it. And I wouldn't use this. It's a great general purpose pattern, but I'm not sure I would use this for the highly critical application startup information, right? Because then you will need to have a Kafka consumer, you need to start up the Kafka consumer, it can take time. It's probably best just to do like, hey, S3, give me the information back, and you're done with it, right? It's better. So if you have like critical application startup information, I would probably go with the first pattern and not this pattern. Okay, great. We've reached our final pattern for this talk, which is the HTTP reverse proxy cache. This is like the biggest one in terms of scale. So at Wix, it's really important for us to have the best experience for our Wix website owners, and even more importantly, for their visitors to their sites. We want them to have a great experience and really fast experience. So for that, we had to optimize all of the site rendering that we had. So a few years ago, we switched to render our sites on the server side, so server-side rendering. And that, of course, means better rendering because we have limits, especially on mobile applications, on the amount of compute power that mobile browsers have in order to render the site. So in order to render it and just bring back the HTML from the server will definitely be faster. But it still takes compute power, it still takes time. So, and of course, our sites are visited millions of times every single day. So there's a lot of opportunity here for caching the results. So Wix deploys Varnish caches all around the data centers, and they are put right in the beginning of the data center, right after DNS resolution and load balancers, and the Varnish cache is hit. Now, if the site was already cached, then the response will get back immediately from the Varnish cache, the HTTP response. And of course, if there's a cache miss, then Varnish cache will forward the request over to the site rendering service. So that's why it's a reverse proxy. It processes requests, but usually the request will stop at the gate of the cache, and the response will return immediately. Now, this, of course, is a very simplified flow. There's a lot more steps when you enter a Wix data center, a lot more security balancing and stuff like that. And I also mentioned that Varnish cache is open source, so you can check it out yourself. Now, what about cache invalidation? And here it is very important. We're talking about this huge scale, and we have our sites being updated from time to time by the Wix site owners, that the old versions of the caches are invalidated immediately, and our site visitors don't get stale sites, which will be really, really bad. So how we do that is that each component that publishes updates to the site, especially the editor services, when they publish a new site version, they emit a Kafka event that there is a site published purge request with the site ID. Then we have a dedicated Varnish purger service that gets this site ID in the event. And then it goes to all the Varnish caches and it requests to get information, and then it will say, hey, do you have a cache of this site ID? And if Varnish cache says yes, then it will get a delete request. And the way it works is that each HTTP request incoming to render already has an E tag with the site ID. So it can be perfectly matched to the purge request. And now that we purge the site ID, Varnish cache will not have this cached HTTP response. And the next time there will be a request for the site, it will go all the way through to the site rendering service, and the new version of the site will be cached, which is exactly what we wanted. And let's talk about size limits in terms of Varnish cache, because we are talking about usually a huge scale of traffic. So you have a few options. We have the memory-based option, which means that all the Varnish cache are put in memory, but that means you're probably going to have to pay a lot of it to have big memory provided to you by your cloud service. Now, if you want to have a less expensive option, you can use a file-based storage, which means it's less expensive because it's stored on disk. But you can have performance penalty because of disk space fragmentation. Now, Varnish does offer the third option here, which is also backed by files, but it has a fragmentation-proof algorithm. This is only for paying customers, not the regular open source version, so it's in Varnish Cache Plus. Great, so to summarize all this HTTP reverse proxy pattern, talking about the type of cache which is read-through, it is put before your applications. And in terms of cache size configuration, it really depends on the backend storage that you choose according to the types I showed in the previous slide. And it's best used when you want to improve latency for relatively stable HTTP responses for external requests incoming to your microservices ecosystem. But I won't use it if you have like extremely complex cases of knowing when your data is no longer valid and fresh. If it's going to be a really, really hard time to invalidate because you have aggregated the data from multiple sources, and it's really hard to synchronize everything, then I wouldn't use this kind of cache. I would use more local caches on each of the data sources that you're going to aggregate. And I've created this very simple flowchart in order to understand the different use cases and when to use each cache. So, is your data crucial for startup? And is not really changes a lot. It's like mostly static configuration data. Then you can just have a backup in S3 and be done with it. You don't have to make it more complex than it is. But if your data is not really crucial for startup and it's mostly, it can change quite a lot, then having the sort of solution like DynamoDB based plus events cache or Redis caches that you can also use the pub sub pattern there. There are quite equivalent concepts with Redis to what I said about DynamoDB and Kafka, so you can check that out as well. So this is like a really general purpose kind of caching. But there is differences between Redis and DynamoDB. I don't can't talk about it in the scope of this talk, unfortunately. And of course, if you have like external clients, so we're not talking about like specific database access optimization. We're talking about external clients to your system that you want to cache the responses. It's relatively easy to invalidate the responses. Then I would go with something like Varnish, reverse HTTP proxy, or also with content delivery networks that provide static information really, really fast. There are a lot of companies out there like Fastly, Akamai that are involved in making sure that data is provided as fast as possible. But of course, it's more expensive solutions. So it depends on your traffic, your scale, and your available choices. Okay, so I have a more in-depth coverage of all these patterns in this blog post that is like where I started talking and writing about all of this a very important issue of caching optimizations. And I also wanted to make it to share a little bit about Greyhound. So we have our own Kafka high-level SDK used by our 2000 microservices at Wix called Greyhound, which has a lot of great features like parallel consumption whenever you're parallel consumption whenever you want to constrain the amount of parallel work you do in your specific service instance, or actually increase it. It's a much trickier to do with regular Kafka SDK, but with Greyhound it's really, really simple. Batch consumers with Greyhound, so you can easily do higher throughputs and bulk APIs, and more resiliency with all kinds of retry policies to make sure that consumption and producing of messages in your event-driven system are eventually successfully processed, and all kinds of other great features. I really recommend for you to check it out. And I put all the slides on SlideShare, so all of the links, so you can just check out Natan Silnitsky on SlideShare, and you will find these slides. And I want to thank you very much. And you can also follow me on Twitter and LinkedIn to get all kinds of updates on all the infrastructure that we have on our team on Kafka, event-driven style of development, key value stores, caches, all around these data stuff for backend services, and software engineering in general. And you can also find blog posts and previous talks I gave in conferences on my website at natansil.com. And if there are any questions, I would be more than happy to answer them.
Thank you, Natan. So I'm looking at Rocket now. If you got questions, now is the moment. You get the Q&A section that you can use. There is a little delay in the streaming, so let's wait a little bit.
Sure. I can also, if it's interesting, I could also discuss the difference between using DynamoDB solution and Redis solution, if that's interesting.
For sure. We got a couple of minutes for that. So.
Okay, great. So at Wix, we decided that we want to have the fastest cached response possible. And that's why we chose to have these in-memory LRU caches. So that means that you can't be faster than just getting the response in memory, right? Now, if you go with Redis, usually it will mean that you have a Redis cluster of the cache, which means an extra hop. So it's in the same data center. It doesn't provide too much added latency. It's not that big a deal, but we do have use cases in Wix that this zero latency really improves the overall latency of the system. Because any hop you introduce means worse performance, and also it introduces another failure point, right? Because it is an extra network call. And with Redis, you also need to configure sharding in order to, when you reach bigger data sets, and with DynamoDB, as long as you have equally distributed, relatively equally distributed partitions for your key values, then you don't need to deal with it, and you get like endless increasing scale. Um, so that's the main difference between choosing these two patterns. But Redis is extremely popular as a caching solution. So and it works for most use cases really well. So of course I recommend that.